This is a presentation of the University of Wisconsin Parkside.
So presumably you came here to hear about Mars and the Curiosity mission that's currently going on up at Mars. And some of my students that are in the audience know that if you expect me to talk about Mars, I'm going to talk about something else first. So I'm going to keep with that. And I'd like to vote. And my vote is, do you think Earth is a typical planet? Okay, let's see some hands. How many think yes? Don't be bashful. Thank you. How many think no? Why not? Okay, well, as scientists, we're data-driven. So here's the data. There is currently a spacecraft looking towards the constellation of Cygnus full-time. That's the only thing it does. It watches several thousand stars in the constellation of Cygnus. The spacecraft is called Kepler, after Johannes Kepler. And as of this January, it alone had about 2,500 planetary candidates. Other planet studies had added 800 plus, I forget the exact number right now, it's between 850 and 900 confirmed planets. These are just candidates, but they're pretty strong candidates, about 2,500. And most of them are actually like Neptune. Some are like Jupiter. Some are much larger than Jupiter, maybe 15 to 20 times larger than Jupiter, but still planets. And of Earths, we had about 350. So about 1 in 8 is like Earth. So by just the statistics, most of the planets aren't anything like Earth, whether we want to talk about water or life or anything else. Just even rocky planets are relatively rare. The typical planet is like Jupiter or Neptune, a very different kind of beast than what Earth is. So if Earth isn't typical, why are we interested in Mars? Because if you look at the planets, Mars is smaller, it's farther from the sun, so it's colder, its mass is way less. Being smaller, the planet has cooled down faster, so its magnetic field has gone away. Anything you want to look at, it's smaller, different from Earth. So if we're really trying to understand Earth, well, why look at Mars? And there's a couple reasons. One is, to know one place well is to know all places better. Well, that's what Eudora Welty says. Planetary astronomers say it differently. If you want to know one place, you got to know all places better. Because I can't learn about Earth by studying Earth. I don't know what it means to be a planet by studying Earth. No more than you can study mammals by studying a whale or a camel or a mouse. If I look at a mouse, I don't know about whales. I certainly wouldn't look in water for mammals in that case. So this is a picture most of us have of Earth, thanks to all of our elementary school classrooms, right? And you know, how many of you were disappointed when you got your first airplane ride and you got to fly over Kansas and Nebraska and you realized they weren't green and purple and yellow and, you know. This is a horrible view. This is better. To begin to understand planets, we have to have the right kind of picture in our minds, but to understand our atmosphere, our geology, you can't just study one thing. We got to look at Mars and Jupiter and Venus to get a better idea of what these things are like. But there's another compelling reason. Mars looks like early Earth. Venus is where we're heading, plus or minus global climate change. The The sun alone in 1 billion years will make Earth uninhabitable. And so Earth will begin to look more like this guy than this guy. But early Earth tended to look like that guy. And so Mars gives us a chance to see what conditions were like on Earth 3.5, 4 billion years ago, something of that order. NASA has 4 goals: to characterize the geology, characterize the climate, because we're interested in climate change, determine whether Mars has or ever had life, and, well, you know, we're all budget crunched. Some people would love to go to Mars, and, you know, give or take $10 trillion, we may get there someday. Astronomers are interested in number 1 and 2. But part of what drives NASA and drives the budgets to go there is certainly number 3. If we ever discover life elsewhere, we have to begin to understand our position, our philosophy, our theologies differently. And, you know, Buckminster Fuller once said, "Sometimes I think we're alone, sometimes I think we're not. Either way, the thought's staggering." You have to shape our view of everything by what we know elsewhere. And so maybe Mars has life or had life. That begins to make us think we're maybe a little less unique as humans. To look for life, it would be really nice if, you know, you could just walk up there and meet Marvin Martian. If it were just that easy. But it almost is, because unbeknownst to most of us, when big rocks like the one that hit Russia, or bigger ones, have hit Mars in the past, they've actually kicked rocks off and sent them to Earth. And where some have landed is down here in Antarctica. And guys go out on their snowmobiles across the ice fields there. And rocks are really easy to find because you look for the non-white things, okay? And so here's one of the rocks. This was found in the Allen Hills of Antarctica. It's called ALH 84001. And inside this rock, when you cut it open, here's this little feature here, which has 2 possible explanations. It's either some mineral grain, to which all the geologists are going, wow, that's really cool, or it's a fossilized bacterium. And the jury is still out on this particular rock, okay? Still very debatable as to what it really is. But this suggests that maybe there are fossilized bacteria on Mars, and then you can sit there and say, well, at least maybe there was life, and it gives you some hope for finding current day life. If we're looking for life, and what we're most likely going to find are very primitive bacteria, if we find life, what they need is free water. This is not like the water in the back of the room that's free. This is water that's not combined into other chemical compounds. So it's not tied into calcium carbonates. It's not locked into sulfuric acid as it is up on Venus. It's freely found water, not necessarily running water, but freely available to be used chemically. We need carbon because even though Star Trek has told us maybe we can go find silicon life forms, carbon's still the only way we know how to make this happen. And we need an energy source, which could be things like sulfates. Sunlight could be one form of energy, lots of different things, but sulfates are probably the most likely thing, as we're going to see here in a bit. We've had a number of orbital missions already up to Mars, and I haven't listed all of them, but these are some of the current ones still going on. MRO, the Reconnaissance Observer, is still going. Global Surveyor has done a lot of work, Mars Express. And Mars Odyssey has finished a lot of its science, but it's currently being used as a radio relay from Curiosity on the surface to Odyssey back to Earth. Early orbiters have told us a lot about Mars. The earliest pictures of Mars from Earth are really pretty horrible, and they had all sorts of fanciful ideas. And even the first spacecraft up there showed us all sorts of wonderful things. What you see in this picture is from here over into about here is a gigantic valley that's caused not by water but by volcanism. And this is about the size of the United States from Washington, D.C. to Los Angeles. Okay? So if you think about big canyons like the Grand Canyon on Earth, Grand Canyon is just that little bit as opposed to this whole big thing. Okay? These guys over here, by the way, volcanoes. And there's really no no continental drift, so things like volcanoes just build and build and build and build and build. So when you look at a volcano, this is Mount Olympus. In the kind of Latin form, it's Olympus Mons. And this guy is the size of the entire state of Wisconsin. It is much larger than Mount St. Helens, Mauna Kea in Hawaii. Think of any volcano on Earth, this guy tops it. It is 58,000 feet tall from the surrounding plain. It's an additional almost 10,000 feet above the mean level on Mars. If you don't do the math real quick, 58,000 feet is about 11 miles high, okay? So this is big, really big. And it's because it's been there for billions of years, and every time it erupts, it just keeps getting bigger and bigger and bigger. And we don't know if it's dormant. It may possibly still have the ability to erupt. So, kind of fun place. Here's a surface map where this is the valley we were looking at earlier. That's Mount Olympus there with 3 other pretty large volcanoes there, another set of volcanoes over there. And these are giant impact craters that dwarf anything we have presently visible on Earth. Thousands of craters. And I'll show you some pictures of ones that are recently occurring up there. It's still getting hit by rocks in space. But why I mostly show you this picture is the colors tell you how high things are. And unlike Earth, where we have continents and oceans, of course, things are, land-wise, pretty much the same height. And of course, if you took away the oceans would be depressions compared to the continents. But they're kind of scattered, around the globe. You've got Asia and the Americas and so on as you look at the globe. And it's a very different picture here because you don't have that continental drift. So the southern half here is all highland. It's all much higher. And this is all lowland up here. And if you also look at it, this is all rock, cratered, very heavily disturbed, very geologically active, and not much going on up here. This was probably covered by ocean in the past. And so a lot of the features have been it's not that you don't have giant meteors crashing into the ocean, it's because you had erosion here that changed the surface very drastically. Mars here has an atmosphere. It's a very thin atmosphere. It's about roughly a 90th to a 100th of Earth's atmosphere, but it definitely has clouds. Because it has clouds, it also has the ability to hold polar caps. So there's both a north and a solar polar cap. And basically this whole planet is covered with a very thin bluish cloud in this particular picture. These clouds are still ices like ours are, and those ices come and go, And you also have dust storms, so sometimes it kind of has a reddish haze on it, in this case a bluish haze. The bulk of what you're seeing in this haze and up in the polar caps is not water ice, but carbon dioxide ice. The atmosphere is largely carbon dioxide, and the ices are also carbon dioxide. One of the first measurements made by Curiosity was to actually sample the gases in the planet's atmosphere, and you get 96% carbon dioxide, argon, which surprises most people, but argon is one of those gases like neon that's used in, God forbid, bar signs. And nitrogen is third most populous. These two are a bit of, I wouldn't say a lie, but it's really carbon dioxide that's been broken apart by sunlight. So they're not formed separately. This is really carbon dioxide that has seen better days. So the top three things tell us one thing, that this atmosphere comes to us through volcanoes. And even if we didn't have the carbon dioxide, the nitrogen and argon alone would tell us that we had a volcanic origin to this atmosphere. And this was pretty much what Earth's early atmosphere was like. This is what Venus's atmosphere is like. And Mercury, the innermost planet, doesn't have an atmosphere. But if it had one, it would look like this. When you see most pictures of Mars, they're always very reddish. And everyone used to say, oh, well, that's because there's a lot of iron up there, and iron, when it oxidizes, or what normal humans say rusts, it turns reddish. And so it's just telling you we have these kind of iron-based soils up here. And then what we later realized was that it was actually the dust up in the atmosphere turns the sunlight reddish. And if you took the atmosphere away, it would look like the picture on the right. So this is much more Earth-like in color. And so when we look at soils and we look at rocks and we look at clays and all these things, they look very Earth-like now instead of this reddish red planet view that we used to have. The orbiters have told us that there had to have been water on Mars. Not just carbon dioxide ice, but we had to have water as well. And when you look at the various pictures, these are sedimentary rock layers. If you go into the Grand Canyon and various places, you see these same kind of layerings. The picture on the left is showing you a riverbed here that's meandering through here, and all of these little teardrop islands in here, the only way we know how you can make that is that you have running water. So early pictures show us that Mars had to have not only water, but flowing water and very large amounts of it. And now the problem is, where'd that water go? And being scientists, there's always that person or three that says, are you sure it was water? Okay. Well, to make the story more compelling, more recent pictures have found this guy and this set of features in here actually looks like a glacier, and that the glacier is under a layer of dust and rock. And a similar feature over here where there's apparently a lot of ice underneath the surface here that at one point then melted and flowed this way, giving you all that erosion. So there apparently is a lot of ice, and we're not sure if it's carbon dioxide ice or water ice or a combination, but a lot of ice up there, and that's at least where some of this water may have gone. We've recently sent a spacecraft up to the North Pole. It was named Phoenix. We'll get some pictures from Phoenix in a bit. But as the orbiters go over the North Pole, you see very much what you see up in Greenland, or used to see in Greenland before it started to melt away, and also down in Antarctica, where you see all of these layers of ice having been set down. And this is, as we get a chance to study that in more detail, that'll tell us a lot about climate change through the years, through the millennia up on Mars. This is a recent impact, by the way. One of the beauties of having the Reconnaissance Observer, Odyssey, various of the other orbiters up there is we have tons of pictures. This is kind of like Google, but for Mars, that they take all these pictures, and one day, this looks very nice, and they come back later and bang, something smashed into here, and it's now created a new crater. And all these streaks is all that material that blew out after the impact. These are all bigger than the rocks that exploded over Russia, and probably about the size of the other ones you hear in the news reports that, oh my God, this is a 600-foot rock, and if it hit Earth, we would kill the dinosaurs all over again if we had dinosaurs, okay? Whatever the latest news story is. Of the landers, we tried to send the polar lander up there. This is a famous spacecraft where they miscalculated the conversion of kilometers to miles. So yes, math is important in education. And they totally missed the planet as it went by. Phoenix went up to the North Pole. Viking 1 and 2. So all of you young people don't know anything about Viking, but all of us who celebrated the bicentennial of the United States back in 1976, that's when Viking 1 and 2 got up there. They're not active anymore, but they lasted about 10 years. We sent Pathfinder up and had the tiny little Sojourner rover. So the last three here are rover projects. Sojourner was the first that says, yes, I can, yes, I can. Spirit and Opportunity were very effective, especially considering they were built to last 90 days. And Opportunity is now up in the thousands. It's gone for a long time. And Opportunity's still going, by the way. Spirit kind of finally got stuck and they turned it off reluctantly. But Opportunity is still going on and on. And the formal name for the latest rover is the Mars Science Laboratory, but it's been named Curiosity, and the only people who use the Mars Science Laboratory name is NASA, as far as I'm aware of. So here's where they ended up. Viking 1 and 2, we'd never done it before, so they found really flat, easy places to put them, because you don't want to really do anything too adventurous with your first ones. Phoenix was purposely put up by the pole, so it was in the summer in kind of bare ground, and then as the winter came on, it got buried in the ice, and there was a tiny chance that after the next summer came, that it would thaw out and we would hear from it again, and I'm sorry to say that didn't happen. That would have been exciting. But apparently the ice kind of tore it apart, or at least its radio. And then Pathfinder was in a place not too far from Viking. Spirit and Opportunity were in slightly higher and a little more difficult terrains. And then when we had a chance to send up Curiosity, Curiosity went into a specific place that would give us the most chance to see the change in geology through the millennia. And then also, because of that change of what we think was wet Mars to dry Mars, the best chance to look for life. So here's the 3 generations of rovers. This is the Sojourner, little tiny thing. This is Spirit and Opportunity. They have solar cells to give it power. And you have these masts up here for cameras. And generally, you have 6 wheels to help you get over obstacles. Now, this particular rock here would completely stop Sojourner. Spirit and Opportunity would have a hard time going over that rock, but this is now Curiosity, and it is not quite the size of an SUV, but it's considerably larger. And to give you an exact idea of the scale here, from end to end here of the picture is about 10 feet, and that's the size, the length of Curiosity. It's quite a big quite a big thing. So Spirit and Opportunity have told us a number of things. Picture on the right shows you the famous blueberries, they're called. These are hematite balls, or spherules, if you like the geology term. They're little round balls of iron that only form in the presence of water. No other way you can make that particular mineral that they have. The rock on the left has all these striations in here, again, telling us about sediments and flowing water, and having much more direct evidence now between the spherules and these rock forms, lots of concretions and strata forming that's more confirmatory of water than just having, some flowing thing you think was made by water. This is coming from Phoenix, and I recently saw a lot of these kinds of ice forms. This is soil-covered, dust-covered ice, and the melting and freezing gives you these hexagonal forms. And you can see this out in Lake Michigan over the winter, that you get these little pieces of ice, and as they freeze and thaw together next to each other, you tend to get these hexagonal forms because that's the most efficient way to pack them into a space. But being scientists, that's not good enough. So Phoenix had a scoop, and it could actually dig down into the soil, and it uncovered water ice. Not just ice, we can actually measure it and tell that it's water ice. So Curiosity. This is a really exciting project. And I wish I could tell you all the great things it's discovered so far. But it's a 2-year program. And they're taking things very slowly. There is a drill at the end of one of the arms on the spacecraft. And the plan is to be able to drill into rock and then be able to sample the material in the rock and not just what's on the surface. And after you've spent a few hundreds of billions of dollars to get this up there, you don't want to be the guy that drills into rock and then gets it stuck, and then the spacecraft can't go. It's trying to drag the rock, across Mars, going to the next place. Okay, you don't want to be the NASA guy to do that. Okay, if you heard about Mohawk guy, from the landing, you don't want to be drill stuck in rock guy. Okay, so they're taking things very slowly. They're unveiling each of the instruments kind of slowly, so as they get to different terrains, because it's already moving, it's traveling to where it wants to go, but it's a very slow process of getting this camera working, getting this chemical analysis working, and then we drill a rock, and then we've got to actually make these things happen and then test this thing, and that takes a week for that analysis. And so it's been a very long story, but we're getting there, and it's a pretty cool place. Let me point a few things out as we got this picture here. There are 6 wheels still on here. The wheels are kind of cool because they have JPL actually written into the treads in Morse code. So as the wheels turn along, they leave behind, dot, 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 and it just spells out JPL as the wheel goes along. They're separately articulated so they can go over rocks and so on. The power is now provided by radioactive materials in the back here. So as they radioactively decay, the heat energy given off by that is converted into electricity, so it can go through the winter, go through the summer, and not have to be kind of parked for the winter like Spirit and Opportunity. This is called mast cam. So it has 2 lenses up here, wide field and telephoto. And this is the ChemCam, which we'll come back to a bit later. There's 17 cameras on this thing. So you have ChemCam, you've got the wide-angle telephoto pair, and then there's a, and you can't actually see it in here because this turret was actually used to take the picture. So the way they stitched it together, it doesn't actually show up. but on the turret there's a very high resolution. It's kind of like having a magnifying glass and going out looking at rocks with it. So there's the hand lens imager, as it's called, and then most of the other cameras are either up here for navigation or in the front and in the back to make, this is your backup camera, on your SUV. Make sure you don't back into a rock or something as you're driving along. At landing, this was 14 minutes away from Earth at the speed of light. So if you're driving along and you've got the joystick, down in Mission Control in Pasadena, California somewhere, by the time you realize that you're going off the cliff, you already have, okay? So they has all these has cams in there to be able to stop it from doing anything, be able to stop on its own. The turret also has a drill in there. It has some scoops and things, so it can scoop soil, drill rock, and then it can get it to 2 devices in here to analyze the composition of the rocks. And so these are the ports here that allow you to get that in there. And then you've got various antennae back here, and there's some radiation detectors and things in the back as well. Most of the action is in the turret. And the second most important thing after the turret is ChemCam up there. So here's where we're going. This is Gale Crater, G-A-L-E. And where it landed is in, I can barely see it. It's in this green oval down here. And the actual spot it landed is basically right about there. So they landed in these kind of relatively flat lands inside this crater. But where this crater was located is that this should have been underwater at one time on Mars. And some of the geology here suggests that of how this is filled in. But the idea is that we're going to try to go from here towards the center of the crater. This is called Mount Sharp. And they're trying to, track their way through the foothills here up as far as they can go as long as the rover works. And as you go to different places, you're going to see different times in Mars history. Okay, but we're going there mostly because there should have been water there, and then it dried out, and you're going to see that change in geology. Curiosity launched on the 27th of November, and I had to tell you, this was the most nervous day in my life. And my wife's not here, so I can say that. Childbirth was probably number 2. But this was one of the more nervous days of my life. Because they were doing something they had never done before. We've landed landers or rovers using parachutes on Mars. But this is 2,000 pounds. The Spirit and Curiosity missions, the rovers, were about 400 pounds. So this is just so much more massive that a simple parachute in the thin atmosphere of Mars, we would have made a crater, okay? You would have Curiosity crater and not a lander. So they did this kind of hybrid thing, which really looked good on paper, and all of us were just really hoping that the engineers got it right. So you come in with this flying saucer-looking thing that's got a heat shield, because even though the atmosphere is thin, it's still enough that when you're coming in at about, well over 1,000 miles an hour, the friction with the atmosphere would burn this up. So there's a heat shield in there, and it's really in this little clamshell thing. And then you get down to a certain point, and it's about 6 miles high, traveling about 900 miles an hour when the parachute deploys. And it's a pretty big parachute. And that's going to slow it down until at some point you kick off the bottom, this heat shield, at about 4 miles. And you're going to keep falling, and somewhere around 1 mile high, the top part of this with the parachute comes off, and now you're left with this little crab-like thing that's got rocket nozzles at the 4 corners. And that's going to fire those rockets and then do a retro rocket kind of descent and try to slow it down. And as it's slowing down, at a certain point, it lowers the rover down on cables and tries to set the rover down on the cables gently, was the hope. And then once it gets the signal that's a, yes, I'm on the ground, hopefully not before that, it then releases the cables and the descent stage flies away and crashes into Mars someplace else. Okay? And that's the hope. Okay? Well, it just so happened that the reconnaissance orbiter was passing over just as Curiosity was coming in. And so here's a picture of the parachute and the clamshell stuff down here. Parachute up there, clamshell down there. And so yes, it really happened, and they could watch some of this as it was going. And then this is an artist's conception. There was a camera on, in fact, it's right about here. There's a camera here that was called the descent camera, and you can actually watch this movie. It's not really a movie, it's a collection of stills. And I decided not to show it tonight because this is like your first home movie and you didn't quite know how to use the camera, and you spend half the time looking in the camera and all these things. It's not the greatest movie ever made. But you can actually watch it descending down towards Mars, towards Gale Crater. So the descent stage up there, a couple cables coming down, and a communication cable, so this guy can tell it, yes, I landed, and this guy will go blast off and go somewhere else. So here's where we landed. Pretty flat place, so pretty easy to set the rover down by the descent stage. And then this is kind of where we're going. These are the foothills of Mount Sharp. And that's kind of the direction the spacecraft is going at this point. And this is not on Mars, but we do have some pictures. This is the turret down here, and there's an arm here that has a whole series of joints that you can turn everything and move it around to all sorts of different rocks and get the different parts of the turret with the cameras there and the drills and various things oriented so they can do what they need to do. And then if they're scooping up dirt, they can then lift it up, turn it around, drop it back into the rover, into the chemistry experiments. Okay, so quite involved. And by the way, as we look at kind of the route of where it landed, at a site called Bradbury, after Ray Bradbury, the sci-fi writer, it's made this path here. This is about 100 meters, that's about a football field. So we've gone actually quite far already. We're on about, I should mention that Mars spins around almost as fast as Earth does. We go around 24 hours. They do it in 24 hours and 39 minutes. And that 39 minutes is a real pain, because if you're trying to track day and night cycles there, the scientists here have to be on that day-night cycle, and their day-night, it just screws up all your circadian rhythms. So these guys actually have to work on a 24-hour, 39-minute day that's rotating through. They basically, for the first 90 days, say goodbye to their families because they have no idea what time zone they're in, what they're doing, and go to school programs. Oh, I don't know, is it day or night on Earth? We don't even know. So the first 90 days is pretty tough on them. We're currently around 214. They're called sols instead of days. So we're at about 214 sols at this point. And this map kind of shows the first 150, I think it is, on here. They spent a lot of time in here because there's a lot of interesting geology and rocks and things that they're using to test out and calibrate instruments and so on. But what I really want you to see is this temperature scale, which you can't read the scale of, but I'll tell you what it is. The temperatures are running, and I know you're all Celsius compliant, minus 16 to minus 95 Celsius, okay? And what that really tells us is that temperatures here are going down to minus 140 Fahrenheit. The average temperature is around minus 35 over the planet. So this is cold. And if you think about the engineering, you know, what happens if you get that little thing that says, you know, the computer battery needs to be replaced? You know? So you have two computers. In fact, one computer, computer A, as it's so uniquely called, already failed. It failed just this last month, and they've already swapped over to computer B, and now they're trying to figure out how to fix computer A remotely so they can use that as the backup. But if you think about it, I've got to move this turret around. And what do I have in all the motors and gears? I have grease that has to work at minus 140 degrees Fahrenheit. You know, just think about how your car turns over in Wisconsin when it's 10 below. You know, whir, whir, whir. I hope it starts, I hope it starts, I hope it starts, okay? And this is what it's working in, day and night. And we'll see why we have to work at night here in a little bit. A lot of the interesting things so far have made the geologist really tickled. Mars on the left, Earth on the right. We are seeing concretions. We're seeing conglomerates. We're seeing exactly the things as Curiosity is going up this path. It's an old stream bed. Exactly the things you see in Earth stream beds. The same kind of rocks, shape of rocks, types of rocks, the concretions, you know, that are making round things out of holes in other rocks, and then the conglomerates where they're getting stuck together by sediments and so on. You're seeing spherules in here. These are actually concretions rather than the blueberries that Opportunity and Spirit saw. And we also get to see sulfate veins, which may be hard to see in the picture, but you see these little white streaks. This is where various minerals dissolved in water and then basically got captured in these little cracks in the underlying rock. We're seeing things that, to me, because I'm an astronomer and not a geologist, kind of looks like shales and you know, pieces that have been broken off that look very much like the rocks you see in these other kinds of strata. And more sulfate veins coming through here, and all sorts of sediments. The soil up here is interesting because you get a global mix of fine dust and then local sand grains, so you can actually sample all of Mars and local Mars simultaneously if you can separate those two out. Okay, I don't know if this is going to show up real well, but one of the experiments uses fluorescence to actually look for chemical changes. So if I take a little light source and I take something that will fluoresce, so I get the energy from this, but then this material gives off light that is characteristic of its chemical composition, I can get, you know, kind of different behaviors depending upon the material and size of the material that I have, okay? Kind of cool stuff. And there, you know, this is blue, and that's definitely not blue. So that, you know, that object is shining at some color that's characteristic of that material. And this is one of the things that the hand lens imager can do. It in fact has an LED just like this one. And so we take a rock, and they actually drove over the rock to get rid of the dust and stuff over the top, so they scuffed it up really good, and took a picture during the day on the left, and then the camera has this little LED on it, and then you can look at the fluorescence of this, and that helps you figure out what the minerals are and what the rock's made out of. And it's much more startling on a computer screen than it is up on the projector, by the way. But we have to do that, the right side at night, left side at day, and if you're doing many rocks, this just takes a while. ChemCam has a laser in it, and it's a pretty powerful laser. So that laser fires at a rock, vaporizes part of it, and then the rest of the camera there is actually a spectrometer. It'll analyze the light given off by the gases after the laser hit them, and it can analyze what it sees. And it's pretty precise. It's a very highly focused little laser dot. So there's one dot. The circles are way bigger than the actual dots. And so you could actually target a particular rock grain or one of these sulfate veins and measure just that and not the entire rock. So ChemCam is going to be really important. And they've already figured out that one of the rocks they saw is not only coming from some kind of magma, but it's a magma that's water rich. So they've already analyzed that. And they're also finding out, for geology students in the audience, that what the composition feldspar is, which surprised me. I'm pretty ignorant about geology on Mars. But how much feldspar they had there, and it had a lot less magnesium and iron than they thought it should have had. So they're already getting a really good idea of the actual rock chemistry for the first time on Mars. Not just guessing at it or having a vague idea of it, getting very specific information. This is the scoop. So we can actually come in there and scoop. And geologists know that if you have a shovel and you're going to take a soil sample, you actually take several soil samples. The first one that you take is used to clean the shovel. So if it had contaminants on it, the first scoop you scoop out, you throw away, and that kind of cleans the surface. And then you take another one, and if you're smart, you take a third one and compare 2 and 3. And so they actually did a number of scoops here, partly to clean off all the earth contamination, partly to clean contamination from other scoops they've made. So they did a number of scoops. And you notice how long it took. They sat there for about 30 days because you're trying to put the scoops into the chemical analyzers, and then it takes a number of days for the analysis to happen and so on. So they were here at this one spot for some time. So there's 2 instruments. One's called SAM. It's the sample analysis instrument. And then they have ChemMin, which is the chemistry and mineralogy instrument. And they do slightly different chemical analyses to see what's going on up there. Okay. So there's one of the scoops it made in the dirt. I know that's an exciting picture, followed by the exciting picture of the scoop itself, but this is real science and everything like that. And one of the things that they're finding out already is that these soils are like weathered basalt. And think basalt is like lava coming out of the volcanoes in Hawaii. These are like the weathered soils of Hawaii. They look red and not black as it is in Hawaii, but they're very similar in composition and chemical composition. And they have the ability to put some of the soils on this observation tray, and there's various other things they can do with it. And they can move it over. This is the actual port. This little flap will lift up, and then you can drop the soil down into SAM or into ChemMin there and have it analyzed and so on. Another picture of the rover with the turret here, and this has actually got the drill interacting with that rock there. So as I drill the rock, the flutes of the drill will bring the powdered rock up and then send it through this instrument and collect the powder so that it can then stick that off into the chemistry analysis parts. And so it kind of comes through the drill part here, winds its way through this guy. This is the hand lens imager here. And they've got, I always love this, NASA has to call it the dust removal tool. It's got a little brush, okay? It's the dust, you know, and knowing NASA, they have to abbreviate it as the DRT, but it's the brush. And then they have another instrument up here. This is the alpha particle X-ray spectrometer. It shines X-rays at rocks. Rocks absorb those, and then they re-emit X-rays according to their chemical composition. So we have all sorts of ways to really refine the chemical composition of these different materials. So here's where the drill first went. It was an area called John Klein. The line there kind of shows you how big this is. This is basically a riverbed, a very flat sediment area. John Klein was a NASA deputy project manager who died in 2011, and so many of the rocks and areas are named very eclectically, you know, like they see a bunch of rocks together in one place, so they call that rock nest, but they name other rocks after individuals and so on. So very sedimentary rocks in here. And the drill came in and drilled 2 holes. A test hole, because you didn't want to be the guy to get the drill stuck in the rock. And it also cleared the tip of the rock off. Excuse me, the tip of the drill off, so you weren't going to contaminate your chemical sample with earthbound stuff. This is the actual test hole, and this is about 2.5 inches deep. And it looks way bigger than it does in real life. It's probably about a 1/2 inch across in real life. Okay, now, fun part. Red, which is the surface covering, gray, which is what the inside of the rock looks like. So our red Mars is actually gray Mars. Very different way of, you know, my entire life in astronomy up to this point, and I've been looking at these things for about 50 years at this point, gray Mars was never in our vocabulary. Thinking about gray Mars is going to be the way to think of Mars in the future based upon curiosity. And this has to do with the level of, if you want the techie word, oxidation, or rusting of the iron compounds, if you want the little less techie version. They took this soil and yesterday released the results. So if you're interested, the New York Times, which is available on campus, page 3 of today's Times tells you about these results. Now, these are brand spanking new. They took that soil, threw it in SAM up on the rover, and heated it up. And it tells you a little bit about how hot, went up to about 1,500 degrees, to release the gases in this material. And what you see are a lot of things that we expected. Carbon dioxide, oxygen, because you have carbon dioxide, water, oh my God, lots of water, and more importantly, sulfides and sulfates. And from that, they've already concluded that Mars is a way better host for life than we ever imagined before. So we didn't know about the sulfides and sulfates, at least in these concentrations. That means, in slightly less technical words, is that instead of being a very acidic environment, this is slightly alkaline in the environment, which is better, it's either neutral or slightly alkaline, which is more conducive to having life. The amount of water is very stunning, and we've gone from being kind of neutral to a little skeptical about how well Mars might have hosted life to now sitting down and saying this would have been a good place some time back to form life. And if you look at where the water is below the surface, it may still be a very good place for hosting life. These are Earth-based sulfur lovers. One of the things that we were looking for originally on Mars was to look for methane, because the early Earth bacteria produce lots of methane. They're called methanogens. And the methanogens really produce lots and lots of methane. And we see almost no methane up on Mars. Now that could have been that all the life died off, and the methane will be destroyed by sunlight in about 300 years. And so it may have had life, it died out, and the methane went with it. Or, what's more likely to be true is that these guys aren't the same early bacteria that we have, that these are sulfur-based, and you're not going to see that methane. And now that we know to look to the sulfates and the sulfur compounds, we're going to have a whole different picture on Mars. Okay? So if you'd like more information about Curiosity, here's some websites. Sky and Telescope has a news column, which is excellent. Mars Science Laboratory has its own JPL website. And if you're into the social media, Foursquare actually tracks its path over the surface of Mars for you. And if you have questions, I'll be happy to answer what I can.
Right.